Okay, let's continue our discussion about transmission line circuit with short termination. So we have already derived the general solution for short terminated transmission lines. So as you can see from here, you have the total voltage and total current on the line, which are a function of the distance d. And as the equation suggests, you have two components, the forward-going and the reverse-going component, which are labeled as V plus and the V minus part. And because of the short termination condition, the reflected voltage is the same of the same magnitude as the incident voltage, while the polarity, the phase, is 100 degree out of phase. Therefore, the two components can be combined as a sinusoidal function of sine beta d, as shown in the equation. And similarly, the current, this current signal can be combined as a cosine function of cosine beta d. So as the result suggests, they are both function of distance, and they are however, you know that there is a phase difference of 90 degree phase difference, because one is a sine function and the other is cosine function. And if you take in the product of the voltage and current, you can end up with the power function P. And in this equation, we represent the result in terms of the instantaneous form. So the time domain response, sine of omega t plus theta and cosine omega t plus theta are shown in the equation. And with some manipulation or massage with the equation, you have location-dependent function and the time-dependent function of the two. However, you know that similar to the previous result, the power function, the location description and time domain description are separate into two sinusoidal functions. Therefore, they cannot support a traveling wave. They cannot support a traveling wave. And as the plots shown in the following figures, we will see that they can be viewed as the so-called standing wave, which is formed with both forward-going and reverse-going components of the same magnitude. So that's the basic condition required for forming a standing wave. And here in this plot, you see the voltage waveform of the standing wave on this short-terminated transmission line at a different time instant. So the numbering 1, 2, 3, 4, 5, labeling the time instance of 0 degree, 45 degree, 90 degree. So which means for a specific position, for any location, the voltage still goes up and down in terms of which can be described as a sinusoidal function. However, at the different locations, the maximum level of the voltage are different. At some points, at some locations, the voltage swing can reach maximum, such as in the middle over here. However, there are other locations that there will be no voltage variation, such as the short termination position. And here's another position with no voltage variation. And this position is reversed as a voltage dual, a voltage node, 电压的节点。所以终端复杂的地方，因为短路的边界条件关系，你有电压的节点。但在这个有完全驻波、有 standing wave 所存在的传输线上面，你会看到有其他的地方会存在电压的节点，包含 这一个点，这一个点。那当然你会有兴趣的是，它们的间隔的距离是多少？啊，它们间隔距离是多少？那从前面的那个式子里头，其实是可以推算得出来，哈。从这个式子里头可以推算得出来。So for the voltage node that is satisfying the sinusoidal function sine of beta d, as long as beta d equals to 0, pi, 2 pi, integer multiple of pi, then the position d shall satisfy the condition for achieving voltage node. So we can simply derive the result. We can write up the result as beta d equals to n pi, n can be ranging from 0, 1, 2, 3, or the integer number. So substitute beta as 2 pi over lambda times d equals to n pi, then you can have d equals to 2 lambda over 2 times n. So if n equals to 0, it refers to the very right end of the transmission line, that is your short termination location. So the next one will be a distance happens to be half wavelengths away from the short termination. And the next one will be n equals 2. That will be 1 wavelength away from the short termination. And the third one will be 1.5 times lambda. Now, so that will be 1.5 wavelengths away from the termination. So the node and the minimum, the voltage minimum, which are the nodes, and voltage maximum will appear alternatively along the transmission line with complete standing wave. So this node refers to voltage node, which is satisfied as sine beta d equals to 0. And similarly, you can write up the equation for current node. And as you expected, they should satisfy the condition of cosine beta d equals to 0. Then for a cosine function to be equals to 0, then the beta d argument need to satisfy the condition of pi over 2, 3 pi over 2, are multiples of pi over 2. And then the corresponding distance on the corresponding distance for current node will appear at d equals to quarter wavelengths, d equals to 3/4 wavelengths, and so on and so forth. And because the power function, P, is the product of voltage function and total voltage function and total current function. So as you can expect it, the frequency for the node appearance will be doubled because voltage node will contribute in the as power node as well as current node, which also contribute as power nodes. So you see the distance between successive power nodes will be quarter wavelengths. Lambda over 4 quarter wavelengths. Right, so that's the voltage, current, and power variation on the short terminated transmission line. And next we can check up with the result of the formulation of a standing wave. Okay, let me move on to the next reason by in section 7.5 we will continue to discuss the some lesson mechanism of the on the transmission line. All right, so as we already observed, if there is the so-called complete standing wave, you will observe zero amplitude for voltage and the currents, so they have the so-called voltage node and the current node. And they are the result of short termination. And there are other conditions that can produce the so-called complete standing wave, includes short termination, open termination. And if you terminate the transmission line with an inductor or a capacitor, because inductor, capacitor, short circuit, open circuit, they do not dissipate energy on those termination. So they all form complete standing wave. So what are the conditions to, how about you have a resistive load? Now, if you have a matching load, that is, you don't have impedance mismatch or impedance discontinuity on the transmission line, you will have no reflective signal. All the incident signal goes into the termination. Now, then in that case, if you have a matched load, you will see no standing wave. How about the case in between? Between the matching node and the short circuit, open circuit. If you have a resistive termination, and the resistance of your load terminator, the terminator is not the same as the characteristic impedance of the transmission line, what happens? Some of the incident energy goes into the termination and some get reflected. So you will have the so-called partial standing wave, partially standing wave. So you will have V minus components. And however, if the V minus component is smaller than the incident wave, then you will have you will not have a complete standing wave. You will have a partial standing wave. So the signals reside on the transmission line. Some are reflected back and some goes into the load. So that's what shall be the more general case. All right? And so in the previous slide, I have already mentioned that according to the power function of the on the transmission line with complete standing wave, it looks like this, and it literally delivers no energy into the transmission line. Here's another proof. If you taking the so-called time average, you see that this mark refers to time average of the signal. So if you take the time average of the power function, P as a function of D and T, and you integrate over one period, that is T equal to 0 to capital T, that's one period, and divided by the capital T, the period, then you will have the so-called average power on a specific point. If you're taking the time integral of the function, so first you get everything out of it, which are not time dependent. So the only time dependent part is this sinusoidal function. And you take the time average of it, and what is the result? The result becomes 0 because the time average of sinusoidal function over a complete period equals to 0. So, and this result is valid for any point on the transmission line, not only for voltage node and the current node. Any other position on the transmission line shall yield the same result. That is the time average of power on the transmission line is 0. So it's valid anywhere on the transmission line. All right, so here we discuss here we will take a further look about the voltage, total voltage, and total currents on the transmission line. As we already know, they are function of this 2J times V plus psi beta D in this. And if you take in only the magnitude, if you get rid of the phase information, you take only the magnitude, you can see that the two signal, the two function, differs by what? Differs by Z sub 0, the magnitude of Z sub 0, the magnitude of the characteristic impedance. And one is a sine function, the other is cosine function. So we know that on the transmission line with short termination, they are 90 degree out of phase. They are 90 degree out of phase, as remarked on the slide. And here is the result of measurement, all right? So because in the previous slide it takes the magnitude of the voltage and current signal, so they are all positive. So that represents if you use a voltage probe or a current probe testing on the transmission line where a complete standing wave appears, then what is the line suggest? The line represents the maximum voltage. The line on above represents the maximum voltage observed on this position. So you see some up and down. You can observe the voltage minimum, the voltage maximum. And as the horizontal axis suggests, you see the separation between voltage nodes are having wavelengths, and the distance between voltage maximum are have wavelengths as well. And note that this is the maximum voltage observed on the line. If you do the test in the time domain, so if you using a voltage probe and test on it, you can see you still observe a sinusoidal signal in the time domain. However, the magnitude is smaller than the result of the measure of this position, and it's greater than the result measure at the voltage node. And similarly, if you use current probe, you will get similar result. The maximum currents goes up and down at a different position. However, the so-called current mirror or current node appears at odd multiple of quarter wavelengths. So here we have lambda over 4, 3 lambda over 4, 5 lambda over 4. So this result can be confirmed with measurements. And so as I already mentioned, these observations are still time domain functions. They are at this position. You not only observe a fixed voltage number. You observe there is a sinusoidal signal at this position. You only record the maximum voltage observed at this position. So from plots shown in the previous slides, you probably can conclude some observation. One observation is the distance between successive voltage nodes or current nodes are what? 1/2 wavelengths. 1/2 wavelengths， 半个波长电压节点跟电流节点的那个间隔是半个波长So by observing the voltage node or current node, you can use the result to calculate the wavelengths on the transmission line. And if you know the propagation velocity on the transmission line, you can calculate the frequency or On the other hand, if you know the wavelengths on the transmission line and you know the frequency of your signal, you can do the product of the wavelengths and the frequency, then you will derive the propagation velocity on this transmission line using this relationship, right? And know that this short terminated transmission line is also referred to as natural oscillation due to the boundary condition, due to the presence of the signal, due to the presence of the signal. We observe that, as I already said, the presence of standing wave represents that some of the energy are trapped on the transmission line. And you can do some, you can do the analogy of electromagnetic wave, standing wave with some other physics phenomenon. I will encourage you to record your experience on so-called using optics or acoustics. 在声波声学跟光波光学，这是你个人可以接触到的生活经验。在声波声学的现象跟光学的现象里头，其实你可以找到类比于电磁波共振的现象。So for example, in this graph, we see that if you have a short terminated transmission line and you have a signal source continuous providing the energy, then the energy provided will be trapped on the transmission line with successive groups which are separated by quarter wavelengths. And what happens if what happens? On the textbook, it provides an interesting experiment. Supposing you cut the transmission line at the position of the vertical of the red vertical line, what happens? However, you need to cut the transmission line carefully. As long as you can cut at this position as what can I say? Open circuit. If you cut this transmission line with just and leave it as an open circuit, it won't perturb the voltage signal vibration at this position. And because you cut at this position with an open circuit, and because there is no current goes through this position, so the open circuit does not perturb the boundary condition in terms of current flow. And if you cut at this position, and because this is a power node, and there will be no influence, there will be no difference observed at this position. And as long as the vibrating phenomenon still appears at the left end, and at the right end of this cutting position, then you will feel nothing about this cutting behavior, because the cuts with an open circuit does not affect anywhere else. The oscillation phenomenon still observed, still appear on the transmission line. So you can cut this position with an open circuit, and you can again do the cut at this position with what? is a short circuit, so that the voltage node is not affected, the current is not affected. And at this position, you should do the cut with open circuit. So as long as the boundary condition is not violated, is not affected, you can separate, you can leave the transmission line as the so-called resonator, 共振器 resonator. So that's one way to formulate a resonator. And you know that the resonator only resonates at a certain frequency. For this example, this is a transmission line and at the so-called fundamental frequency, that is the lowest frequency that a resonance can reside on this piece of transmission line, which has a short termination at the right end and an open termination at the left end, which the length of the line happens to be a quarter of wavelength. And this boundary condition and this length can support the resonance of signal at a certain frequency. This frequency is referred to as the fundamental mode, fundamental resonant frequency. And for the same termination condition, if you increase the frequency of the signal, you observe that if the frequency happens to be 3 times of the fundamental frequency, then the length of the transmission line becomes 3/4 of the wavelength. Then the boundary condition can be satisfied, which means that the same piece of transmission line can support another resonance, which happens to be 3 times as high as the fundamental frequency, resonant frequency. And the similar result can be observed for 5 times of the frequency, 5 times of fundamental frequency. And at this time, the length of the transmission line is 5/4 of a wavelength. You can imagine you will have in a higher order mode, at a higher resonant frequency at 7 times, 9 times, and 11 times. Okay, so here in this plot, you observe the so-called fundamental frequency and higher order modes. They are all referred to as natural oscillation, 自然共振. And you are encouraged to find example of natural oscillation, which can be easily found from musical instrument. 这瓶子开口太大了，小一点的话就很好吹。我在表演这个，我还参加过6年的管乐队哦。So what have I done? Well, I try to convert energy from the form of acoustic mechanical flow. So that's, you blow the air, that's take some effort to blow the air, that's a form of energy. However, without this instrument, you cannot make any sound. Well, with the help of the bottle, which provides resonating resonating instrument. Okay, you see, for the airflow, I need to keep the airflow just sweep across the opening. So it's similar to open-ended, as we have seen in the previous slide. And at the bottom of the bottle, which is filled with water, and as you can imagine, the airflow is not that easy at the surface of the water. So it's similar to a short circuit condition. So you have open-ended termination and short circuit termination, and the air blow activity provides the energy. And this instrument, this structure, supports the natural oscillation of acoustic wave for certainly one time that you can hear the voice, hear the sound. Okay, and of course, because there are some attenuation mechanism reside within the structure. So the sound or the resonance can only sustain for some time. That's the reason why when you play musical instrument, you need to the instrument usually come with resonating cavity， 像是什么吉他的那个箱子啦，或钢琴它也是，你去看那个什么 grand piano 啊，它的那个琴声就特别的大，或者是说你看到小提琴啊，提琴是不是有小提琴、大提琴、中提琴？那今天你只要看到一个家伙的那个身材比较大只的话，那他还没说话，你大概可以预期到他说话或唱歌的声音，跟一个卡塞加郎他的说话唱歌声音是不太一样的。为什么？因为大家共振腔大小不一样嘛。好 ，OK， 有的你看到有些歌手他可以声音可以变男变女，那就是他自己操控那个共振的位置的能力比较厉害嘛，所以对啊，所以你看到为什么大提琴的声音比较低，小提琴的声音比较高因为你提供的共振腔大小不同，它能够去 support 的那个 fundamental resonant mode 就不太一样所以小老鼠的叫声跟大象的叫声就差很多嘛OK。Alright, so here's some example about natural oscillation. As you can see here, I show a picture of a trumpet, which is which is among the bass family. It has the highest register. Well, I think the bass family is quite amazing because you only have 3 or at the most 4 valves, but you can play all the notes you can play all different notes with just 3 or 4 adjustable valves. So taking the trumpet for example, the total length of its highest, if you 我忘记了，你要按下去管声才会变长还是变短 ？Okay, each valve increases the length of the tube. Alright, so if you press all the 3 valves, you will have the longest tubing on the trumpet. 可是它中音 C 是不用按的 ，OK Alright, but anyway, so if you look at the size, 148 centimeter. You see that without pressing any bulbs, you can produce pitch C, and you can produce another C with a higher octave. 哆嘛，跟高音哆不是。这是哆啦，高音哆是这个 ，OK， 收也是收也是，然后再上去的高音收，然后再上去的2点哆，OK， and they have the same valve position, so it's I always feel it's really amazing. Huh? So how can they produce the sound of different pitch using the same length of tube? Well, the musician need to control their lips so that the tube, the resonance at the tube, can be excited with selected resonant mode. Okay, so they don't have to change their gesture, the same of setup. But for different pitch, they need to blow the air a little bit harder or a little bit softly so that the different sounds of different pitch can be produced. So I found that really amazing. Yeah. All right, so if you check up with the length of the trumpet, and well, what is the velocity of acoustic sound or of acoustic wave? As far as I can remember, it's about 330 meters per second, something like that. It's a little bit off. And the length of the trumpet is about 1.5 meter with the longest stayed up. And the sound dough is about 440赫兹吧，441赫兹吧。So you do the division of the velocity and the frequency, you end up about something like a 0.75 meter something. So the pitch C or the sound do happens to be in this mode, half wavelength mode of the trumpet. And this is about the same principle that you can find with musical instrument. So at a higher pitch, say at a higher octave, 高八度 higher octave, you get higher pitch of C, higher pitch do. It's the length of the trumpet happens to be about one wavelength of that pitch. Yeah, and similar result can be observed for this. So okay, here is the calculation. All right. Yeah. Okay. For this one, it's 233 hertz. So it's one wavelength of 148 centimeter. And a higher octave in this one, so you see the frequency is double of this one, so it's 466. And the wavelength is shortened to 74 centimeter, so the trumpet is about 2 wavelengths of this pitch. And you can do the math for either, and okay, the velocity of sound is about 345 meters per second. But that's a general guess, the condition. The velocity can be different for different humidity, different temperature, different height, so it's changed. So you see that, so you see that before the performance of the concert, so the leading musician, 也就是首席啦，you will stand up before the play of any song. She will stand up and try to lead everyone to tune the pitch of the instrument. 但是小时候的时候总觉得这是在装逼啦但实际上这个是有效的因为你的那个当天或者那个位置那个演奏厅的声音的速度是不一样的，所以 那表示其实我玩乐器玩得不好了，我这耳朵很背啊，听不出来哈。所以基本上调音这件事情只是在装逼而已 ，OK。但真正的音乐家，我相信他们可以听出来哦，那个 pitch 一点点的那个差异，所以要根据当天的那个情况来去调整一下你的乐器的那个音调了，OK。Alright, so in this slide you see that music is the study of music. About 800 years ago, it's first in the College of Science. So music is actually a science comprising the study of maths and physics, right? Okay, so let's go back to our topics. So let's now consider a transmission line of length L, and if one end is open circuit and the other is short circuit. So what is we know that the two ends of the transmission line are terminated, so if you supply some radio frequency energy, you can store the energy. So the question is, what are all the possible standing wave patterns can appear on this transmission line? So you need to do this, you need to identify the boundary condition. You need to identify the condition. Because one is short-ended and the other is open circuit. So the short circuit determines that the voltage across the short circuit must be 0 at all times. And the currents on the open circuit end should be 0 at all times. So depending on the termination, the short circuit or open circuit, it determines that it's a voltage node or a current node. So you can do this according to the termination condition. And in this case, because one end is short circuit and the other is open circuit, so the fundamental mode should be the so-called quarter wavelength resonance. Because in one half wavelength, but in a quarter wavelength, you can satisfy voltage node and current nodes at the two ends. So the fundamental mode is the so-called quarter wavelength mode. So the length will be lambda over 4, a quarter wavelength of the wavelength of the specific frequency. And the next resonance that can appear on this transmission line of this specific boundary condition is the cell mode, which is 3 times the fundamental frequency, which is 3 times, the frequency is 3 times higher than the fundamental frequency. And for this frequency, the wavelength happens to be, the line length happens to be about, to be 3/4 wavelengths for this case. And as you can imagine, the next one will be 5 times, the frequency will be 5 times of the fundamental mode. Okay, so you have the wavelength and the frequency relationship can be concluded using equation 7.9. So this is the transmission line length and the ratio between the transmission line length and the wavelengths. So if you substitute n with 1, 2, 3, 4, 5, you get a quarter wavelengths, 3/4 wavelengths, 5/4 wavelengths, so on and so forth. 好了，我们先休息一下。